In the previous lecture, we covered the basics of least squares or fitting lines. In this lecture, we're going to cover the basics of inference. So if we have a smaller sample from a population, how can we say something about what our line that we fit in that smaller sample says about the line that we would get if we had the entire bigger population? So again, we have this data that we've collected from, well, Francis Galton has collected on our behalf in the 1800s, and so we load the data in using R package, and we plot the average parent height versus the child height, and then we fit a linear model relating the child's height to the parent's height, and we do that using this tilde term. So the linear model function actually always fits an intercept term unless you tell it not to, and then it assumes that you are including a bunch of other terms that you would like to be included as figures in the line. And so in this case, we only have one other variable, and we're using the mid-parent height. So then we can overlay the fitted values from that line. So we have the values of the parents' heights, and we have the fitted values that we get that are equal to the estimated intercept from this plus the estimated slope times the parent height. And so we've overlaid that specific line in red. And so what we've seen here is actually one line that we got from one particular subset of 928 families where they calculated the mid-parent height and measured the child's height. And so if you look at this fit of the line to the Galton data, we actually get numbers for what's called the coefficients. One is the intercept term, again, so the intercept is 23.942, and then we also get a term for the parent's height. In this case, it's 0.646. And so what this means is that if you increase the parent's height by 1 unit, so in this case 1 unit is 1 inch, you will get a corresponding increase in the child's height of 0.646 inches. Because remember the equation where you have b0, which is the intercept term, plus b1, which is the slope term, times the parent's height. So b1 times height scales the changes in parent's height to changes in the child's height. So what we could do is actually create a scenario where we have created 1,000,000 families based on the fit that we get from the original data set. So what we're going to do is we're going to generate this new gigantic set of data where the data has now 1,000,000 rows. And so what we're going to do is generate the parent's height from a distribution where the mean of that distribution is the average of the parent's heights in the Galton data set, and the standard deviation is the standard deviation of the parent's heights in the Galton data set. And then what we're going to do is we're going to generate child heights from the model that we fit on the Galton data. So what we're going to do is we're going to say that we're just going to make up child's heights that have an intercept term equal to the intercept term in the Galton model. It's the first coefficient value, plus the second coefficient value, or the slope, times the parent value. And so we've actually calculated generated the parent values with this line of code here, plus some noise or some error term, just like we saw in the equation when we were doing least squares, so that all the points don't lie exactly on the line. And then since we've generated 1,000,000 points, it makes it a little easier to see if we use a smooth scatter rather than just a scatter plot. So here I've plotted a smooth scatter of the parent's heights versus the child's height for these 1,000,000 families. And so this is actually the regression line from the Galton data set. And so we've actually generated the data so that this is the regression line that exists in the overall population. And we've generated a bunch of values for parents and child's heights. So what we can do is we can imagine hypothetically taking a subsample of those 1,000,000 families and calculating a new line. So what I've done here is I've set the seed so that I'll get the same answer if I run the code a second time, since I'm going to be doing sampling. And I can sample from our new Galton data set, our 1,000,000 families. I can take a sample of size 50 without a replacement from that data set. And then I can then fit a linear model on that subsample data set. So this is on the 50 samples that come from the sampling of this 1,000,000 family data set. And so what I can do is I can plot the data that I get. So again, I could just plot parent's height versus child's height, and these are the points for parent and child height. And then the red line is actually the line that we got from the original fit of the Galton data. And the black line is the line that we get when we fit the linear model on this new subsampled set of data. So we see that this line is just a little bit different. It's got a little bit different slope, and it looks like it probably has a little bit different intercept than the original line that generated the data. And the reason why it's a little bit different is because we took a random sample. So every time we take a random sample, we'll get something a little bit different. In fact, if we took another random sample of 50, again, we'd see a different set of 50 points where we plot the mid-parent height versus the child's height. And again, if we looked at, this is the regression line that we get, the red line from the original fit to the Galton data. And the black line is now the line that we get when we fit to this particular data set. And here the difference is a little bit bigger, so we see that this line has maybe a different intercept and a different slope. And so every time that we take a random sample, we're going to get a different line. And so since we don't actually have all 1 million families, and in general when we're doing these analyses, you always have some smaller sample of the population rather than sort of a much larger sample, unless you're doing sort of a descriptive analysis on a census. And so you can keep doing this over and over and over again, and you keep getting different lines. And so what you can do is actually do this lots and lots and lots of times. So now I've generated actually 100 different subsamples. So each time I go back to this big population of 1 million families, and I take a sample of, say, 50 families, and I fit a linear model, and I save that linear model into a list. So I'm saving each new linear model into one element of this list. And then what I can do is I can actually loop through that list, and I've generated here now the smooth scattering of all the data points that exist for all those 1 million families. And then I've drawn the red line, again, is the line that generated those data. And then what I've drawn here are a bunch of lines that I get from repeatedly applying this linear modeling strategy to 50 subsamples of size 50. And so what you see is you get a bunch of different lines that have a bunch of different slopes and a bunch of different intercepts. So what you might want to think to yourself is, okay, in practice, I don't actually get to see a bunch of different subsamples. I actually only get to see one of these lines in any given study. So if I only get to see one of these lines, black lines, and it's not necessarily equal to the red line that generated the data, what can I say about the red line if all I get to observe is one of the black lines from a subsample? This is to look at a histogram of the estimates that you get from those 100 subsampled data sets. So on the left here, I see a histogram of the intercept terms, and you can see that they're centered on the intercept that was used to generate the data. And you can also see a histogram of the slope terms from the 100 models that we fit. And again, they're centered on the actual slope that generated the data. Of course, we don't actually get to see either of these distributions because in practice you only get to see one data set. You only take one sample. So we're going to have to try to use that one sample to say something about what these distributions look like. So it turns out that there's a really powerful theorem, and I would say this may be the most fundamental theorem and that's used in all of statistics, but maybe in all of mathematics, called the central limit theorem. And it turns out that in many cases, if the certain assumptions are met, our estimates beta hat 0 and beta hat 1, so this is the estimate of the intercept and this is the estimate of the slope, follow normal distributions. And so this is a normal distribution with mean B0 and with the variance, that's the variance of that estimate. And then also this is actually should be a B1 here, and then the variance of that estimate as well. And so it turns out we might not know what these variances are exactly in a specific data set, but we can estimate them as well. So we end up with beta hat 0 and beta hat 1 are sort of approximately normally distributed with the corresponding beta B0, and again this should be B1, and variances that we've estimated. The square root of the estimated variance for a coefficient is the standard error for the estimate, what's called the standard error, and it's abbreviated S.E dot of the standard error of the actual estimate here. And so what we can do is we can actually estimate those values in R. And so here I've taken a specific subsample of size 50 from that larger million family data set, and I fit a linear model. So again, I've said I'm going to fit a model where I relate the child's height to the parent's height. So recall that the linear model function always assumes an intercept term, so it's going to estimate an intercept and then it's going to estimate a slope for the parent term. So if I do a summary of that object, I actually get the call, what I actually said, told LM that I'd like to fit, and then it gives you some information about the residuals. We'll talk about that later. And then it also gives you an estimate of the intercept. So this is the estimate of the intercept that we get for this specific data set. And it gives you an estimate for the slope of the term for parent here. And then it also gives you standard error. So these are these square root of the variance estimate for this coefficient. And the same thing for this coefficient down here. And then we'll talk about what these other values mean as we go on. So, but just to get an idea of what this looks like, so again, this is the distribution of slopes that we would get if we ran the study 100 different times. And then this red line here is actually the distribution that we estimate, the normal distribution that we estimate, using the estimated slope from the one subsample data set and the estimated variance that we get from that subsample data set. So we see that for this specific subsample data set, the actual slope value is slightly different than the slope value that generated the data, but the variance is actually about the same between our estimate and what the variance is across the population. So why do we standardize variables? So you can see that we're going to be talking about a lot of different variables and a lot of different distributions, and it turns out that we actually are going to be standardizing them very often. And the reason why is we want to be able to make comparisons across variables, but also we want to be able to make our understanding of the distributions easier. And so, for example, both Celsius and Fahrenheit are ways of measuring temperature, but you might convert both of those to Kelvin to both make them comparable across each other, but also because Kelvin is a scale that is easier to understand in some sense because it has fewer parameters that you have to be able to deal with. And so we do the same sort of thing when we do these analysis of these coefficients or these estimates that we get from the linear models. And so you can see, for example, that the intercept term has a mean that's somewhere between 20 and 30, whereas the slope has a mean that's somewhere, a little bit north of 0.6. And the variance is also very different between these two distributions. And so suppose that we want to be able to identify what this distribution is without having to have all these different parameters to specify that this one is, a little bit more spread out and has a much higher mean than this one does. Well, we can standardize the distributions. And so the way that we do that is to take the coefficients that we have, the estimates, beta hat 0 and beta hat 1, and we know a little something about their distribution. So if it turns out if you take beta hat 0 and subtract its known mean value, so this is now the real value if you knew it, and you subtract it from beta hat 0 and divide by the standard error of beta hat 0, this actually has what's called a t-distribution. And it has a distribution that is t with the number of samples that you had in your study minus 2 degrees of freedom. So degrees of freedom tells you a little bit about how much variation you have left over after estimating your parameters. So in this case, we've estimated two parameters, a beta hat 0 and a beta hat 1. So we have a total of n samples. That's how much variation we have to deal with. And then we actually lose 2 of those degrees of freedom when we calculate the mean and the slope. And so similarly for beta hat 1, we get a distribution that is the same distribution, a t-distribution, because we've now standardized. So we've sort of subtracted the mean, we've recentered this variable near 0, and we've divided by the standard deviation, which means, or standard error, which means we've sort of set this variable to have a specific and fixed unit amount of variance. So just to show you a little bit about what the t-distribution looks like compared to the normal distribution. So Here, again, I'm taking all the points, just a linear set of points between -5 and 5 of length 100, and I plot the normal distribution, and so that's the black line that you see here. And then I also plot a couple of different t-distributions. So this is a t-distribution with 3 degrees of freedom. So you can imagine this is the distribution that you would get in red if you had 5 data points and you estimated 2 parameters. And so you can see that it's got a little bit fatter tails. There's a little bit more probability density out here to the left and to the right. And so what does that mean? It means that we're a little bit more we're a little bit less sure about where the center of the distribution is because it's a little bit more spread out. And then if you increase the degrees of freedom to the t-distribution to say 10, you get this blue curve, which is now looking much more like the normal distribution. And in fact, as the degrees of freedom gets very, very large, it's almost exactly the same thing as the normal distribution. So once we have our estimate, in this case beta hat 1, that's the estimate of the slope between the two variables. We want to know something about, say, how good our estimate is, or maybe a better way to put this is we want to know what are the possible values that the real B1 has when we have this B1 hat estimate. So one way is to create what's called a level alpha confidence interval. So a confidence interval is going to be a set of values for B1 that are values that we think are plausible. And they're going to be defined in a very specific statistical way in the sense that a confidence interval will include the real parameters, so the real value of B1, alpha percent of the time in repeated studies. So if we, to think about it another way, suppose that we over and over and over took a subsample of the same size and we recalculated the confidence interval in the same way, then we would get 100 different intervals, and of those 100 different intervals, alpha percent of them would cover the parameter that we actually cared about. So the way that you calculate these confidence intervals is using this t-distribution and using the estimates and the standard errors that we calculate from the data. So we can estimate beta hat 1 from the data using the lm command, and we can actually estimate its standard error as well using the lm command. And so to get a confidence interval, we actually just multiply the standard error by a particular quantile of the t-distribution where we choose the quantile that's equal to alpha divided by 2 if we want an alpha level confidence interval. And so what we do is we do plus and minus that to make a symmetric interval. Actually, this should be minus and plus. I've got this backwards. And so what we can do is, if we look at the coefficients from the linear model, we actually have estimates here, and we have standard errors. And then we can apply this confident function to this same linear model term and tell it what level we would like the confidence interval to be, and it actually performs this calculation for us. And so what it tells us is, in this particular data set, we estimate the intercept term to be 15.86, but our 95% confidence interval is anything from minus 7.80 to 39.53. So these are the numbers for the intercept that if we did the study over and over again, we wouldn't be too surprised to see an intercept term anywhere from -7 to 39. It's a pretty wide range. Meanwhile, we also see sort of the values that we would expect to see for the slope, and we would expect to see anything sort of between 0.42 and 1.119. So these have a sort of very specific statistical meaning in terms of the frequency with which a confidence interval will cover the actual value. And so just to illustrate that a little bit, here's what I've done. I've actually done this same subsampling. So I have that gigantic 1 million family data set, and I take repeated samples of size 50, and I actually calculate the linear model for each one, and then I calculate a confidence interval for each one, and I show the confidence interval in gray for each of the 100 different replicates. So each of these is a confidence interval calculated from the replicate, and this is the coefficient value for the slope. So remember, 0.6 is somewhere around 0.6 is the real value. That's this black line here. And you can see most of these gray confidence intervals cover the black line, but there are a few, this line here and this line here, that actually don't cover it. In this case, it's about 1, 2, 3, 4, 5, 6, 7. So about 7 of them don't cover it. And so we said for the 95% confidence interval that we expect about 5% not to cover it, and we're pretty close to that. So we can see that in repeated studies, we actually get a different confidence interval every time, but that confidence interval most of the time covers the real value that we care about. So those are the values we sort of expect to see. So here's how you would report this in sort of analysis. So in an analysis, you would have the estimates that you get for the intercept and for the slope. And then you would also have confidence intervals for those values. And so what you might say is something like this. A 1-inch increase in parental height is associated with a 0.77 inch increase in the child's height. That 0.77 comes from our estimate of the intercept, or sorry, of the slope. And then it has a 95% confidence interval of 0.42 to 1.12 inches, and that comes from this confidence interval for the slope here. And so what we're saying is that these are the boundaries of the confidence interval that we have for our parameter of interest. In other words, the increase in child height for a specific unit increase in parent's height. So this is the very basics of how you calculate confidence intervals, and in the next lecture we'll talk a little bit about how you calculate p-values.